Suppose x is a normally distributed random variable with standard deviation 12. Use the test statistic x bar based on a sample of size 16 to compute the p-values below. A. The null hypothesis is 50. Alternative hypothesis, mu is less than 50. Test statistic 46. First, before we can compute any p-values, we should verify that we can use the normal model. Since x is normal, that implies x bar is normal. Therefore, in part A, we can compute our p-value. So our p-value, in general, p-value is equal to the probability that x bar is more extreme than the test statistic. Test statistic in this case is 46, x bar equals 46. So, in part A we have a left-tailed test. So what I'm going to do is draw a normal distribution, x bar, which you know is normally distributed. The mean is the same thing as the mean of the null hypothesis, which is 50. And to calculate our p-value, the probability x bar is more extreme than 46, I'm going to draw in my 46 and find the probability to the left. That's the probability of being more extreme than 46 for a left-tailed test. So, that is the probability x bar is less than or equal to 46. So we can translate this into a problem of z in the usual way. Z is less than or equal to 46 minus 50 divided by standard deviation, which is 12 in this problem, over square root of n, which is 16. So this becomes the probability that z is less than or equal to 46 minus 50, which is minus 4, over 3. And on my calculator I get negative 1.33. So we look this up on our z table and we have our answer. Negative 1.33 gives us probability of 0.0918. So our p-value is 0.0918. Next, B. We want to find the p-value again, where the mean again is 50, and this time the alternative is that the mean does not equal 50. Again, we can use our normal model, and again, the p-value is the probability x bar is more extreme than the test statistic 46. But in this case, the p-value is equal to twice the probability that x bar is less than or equal to 46. And you might say, why do we have a 2 here? Well, the difference is, in part A we were dealing with a left-tailed test. Here we have a two-tailed test. So we always double whenever we have a two-tailed test. Always double for two-tail for two-tailed test. So we can draw the picture again if we like, but we know what the answer is going to be. It's going to be the probability that z is less than or equal to negative 1.33, and we know that this is going to turn out to be 0.0918, but because it's a two-tailed test, we're going to double it. Our p-value then, the probability x bar is more extreme than the test statistic, is going to be 0.1836.